Hi, my name is Yoav Artzi, and I'll talk today about natural language understanding and interaction with users. This talk is part of the workshop on interactive and executable semantic parsing in EMNLP 2020. So first of all, I just want to thank the organizers for putting this day together, and I'm looking forward for discussions and questions on the workshop day itself. The focus of the talk today is natural language understanding when interacting with users over multiple terms. And this is a definition of interaction that I picked up from Google that is really befitting to the talk, as communication or direct involvement with someone or something. There are several aspects of semantic parsing and interactive systems that I'm going to discuss less today, including interaction with the world, language generation, or the types of output representation that we use in semantic parsing. The talk will be divided into two parts. In the first part, I'll talk about our work on the ATIS dataset. I'll focus on modeling context from interaction history, and I'll conclude with discussing some of the limitations of the ATIS benchmarks. These limitations are motivate the benchmark I'll discuss in the second part. This is CerealBar, which is a collaborative instruction following game. I'll focus there on how language changes over time as users interact with the system, and how we can do learning to recover from cascading errors. So ATIS stands for an Error Travel Information System. It's one of the most commonly used and oldest benchmarks in semantic parsing. The target outputs are SQL queries, and the focus is really on natural language understanding. And the ATIS abstracts away much of the complete dialogue problem. So for example, it doesn't have generation, and instead it just displays to the user the tables that it gets out of querying the database. ATIS has been studied extensively, most often in the speech community with simplified slot-filling representations, and as semantic parsing dataset, it was mostly studied with linguistic representations, but more recently with the original executable SQL queries. And as well as a context-independent subset of ATIS has been studied separately, where you treat sentences in isolation and not as part of an interaction. The ATIS database is relatively complex, making the generation of SQL in ATIS of particular interest. So the database includes 27 tables that are linked together and with over 160,000 entries. And the queries that you need to generate this database, which I'm visualizing here at the bottom, are relatively long. On average, the SQL query that you need to generate is almost 103 tokens. ATIS interactions often start with a query like this one: show me flights from Seattle to Boston next Monday. And for this simple query, which is context independent because it's the beginning of the interaction, you have to generate this relatively complex SQL query, where when I'm not going to describe this in detail, you can already see that it's relatively long, it's relatively nested, and it joins different tables for flights and cities and days and airports and airport services. Given this, once generating this kind of query, the system executes it, and the way it responds to the user, it just shows the table of flights that it found. And then the interaction continues, and the user asks another query using natural language, the system responds, and so forth. ATIS was a very ambitious and complex project. It was collected over several years at the beginning of the 1990s across multiple sites funded by DARPA. It was coordinated by a group called MedCow, which stands for the Multi-Site ATIS Data Collection Working Group. And the subjects were asked to query the system given relatively complex scenarios. The interaction was conducted using spoken language, which makes the language very different from what we expect in text, and mostly using Wizard of Oz setup. Now, this is a complex process. It was very hard to scale and extremely hard to standardize, and there were variants across the different sites. The core focus of ATIS is a understanding of compositional language in the context of the interaction. And you can see, and if you go back to our example, you can see how, as the user gives an additional request, like on American Airlines, to generate the SQL query to query the dataset, it actually has to take into account constraints from earlier in the interaction, from the first utterance. As the interaction progresses, this becomes increasingly complex. In the third utterance, which once arrived after 7 p.m., the system already has to take into account constraints from two previous utterances, the first and the second one. And further complexities are introduced later on. As interaction progresses, for example, here, the user changes some of the constraints they provided, implicitly telling the system that it should take constraints from the first utterance, but ignore constraints from the second and third utterances. So in this kind of interaction, as the interaction progresses, the meaning of utterances becomes highly dependent on the history of the interaction. And we can distinguish between three types of objects in the history of the interaction: the user utterances, the queries the system generates, and whatever the response the system displays to the user. Because ATIS usually just displays the tables that generated by the SQL queries, we are only going the model I'm going to present today only looks at the first two, and taking into account the previous utterances and taking into account the previously generated SQL queries. So let's see what kind of information we get from the previous utterances. So this is an example of a conversation in the ATIS dataset. The user starts by showing me all flights from Boston to Pittsburgh on Wednesday of next week, which depart from Boston after 5 p.m. Then they continue the interaction. They switch focus to ask about a specific service class. And then finally, they go back and ask about a specific flight. And generating the SQL for that actually requires taking into account all these constraints from the first utterance, which is basically 9 turns in the past. And this is relatively complex and requires us to really retain information throughout the progression of the conversation, even if the user changes focus. So what we see is that relevant information that is mentioned earlier is implicitly requested by a later request, even though the user may change focus during the interaction. So we really need to retain this kind of information. And our solution to it is an implicit model mechanism that carries this information from the beginning to the end of the interaction and is completely learned. Another object that we see in the context of the history of the interaction are the SQL queries the system generated. And here I'm showing the SQL queries for the first user utterance in the example that we were looking at. And what you can see already that within this complex query, there are certain parts that are coming from different constraints. And these constraints, when they are later reused implicitly in utterances, such as the next one on American Airlines, they're actually, if you look at the SQL query, you can see that they are copied as is to the new SQL query. So there is these spans that, there are these spans of SQL that are imported from the previous utterance, from the previously generated SQL queries, been combined and stitched differently with potentially new constraints from the current utterance. So what we see is that segments corresponding to earlier constraints, they appear often as is in later queries. And this is actually an interesting opportunity. So what we do is we have this explicit model mechanism that composes later SQL queries by copying segments from previous ones. In addition for accounting for context, this also allows us to reuse computation. So we invested computation in generating these segments token by token when they originally appeared. Now, as we copy them as is, what we are doing is we are not necessarily using the same amount of computation and reusing the compute which we already invested earlier on. Okay, so how do we put these two mechanisms into a model? So we start with a very simple sequence-to-sequence model. In this case, the sequence-to-sequence model looks at every utterance in isolation, puts it through the encoder, and the encoder generates a SQL query. So the first thing we do is we add a 10-level encoder. This is an RNN that computes a hidden state for every utterance from its encoded representation and is updated at the utterance level. Given a new utterance, like on American Airlines here, we incorporate the hidden state from the previous step of the 10-level encoder by taking it and concatenating it with each word that we input to the encoder. And this basically allows us to interpret each word in a context-dependent way, conditioned on the history of the interaction. The second mechanism is a query segment copying, and this allows us to copy segments from previous queries. So this operates at the level of taking the SQL query that was previously generated, copying from it and giving it to the decoder to potentially generate the next SQL query. And this mechanism operates along using a number of steps. It first extracts segments from the previous SQL query. This is a deterministic process that operates on the expression tree of the SQL, and it's relatively simple. the next thing we need to do is we need to generate some kind of encoding for these segments so we can reason about them during the coding. So what we do is we run a bidirectional RNN over the entire previously generated SQL query, and we take the hidden states at the delimiting tokens of the segments, and you concatenate them in order to get a representation for the segment. Given this representation, it's relatively straightforward. We compute probabilities in the decoder over not only SQL tokens that allow us to generate the raw query from scratch, but also over these segments that are potentially copied from the previous SQL query. Okay, let's quickly look at what these kind of mechanisms give us as far as performance. So what I'm showing here are the notation accuracy. So you take the SQL query that you generated and you execute it, and then you get a table, and you can compare this table to the table you would get from the gold standard SQL query, and then you can compute the accuracy of how many of the records you got right. So what's happening here is the first baseline is a simple sequence-to-sequence baseline without any access to the history of the interaction. It performs okay, but significantly worse than the other system that we see. Once we give interaction access to some level of the interaction history to a sequence-to-sequence model, in this baseline by simply concatenating some of the previous utterances with the current utterance, performance jumps significantly, but by about 12 points. Our full model significantly outperforms this approach by copying the previous utterance from the previous SQL queries and also carrying information throughout the interaction. So we can already see that using interaction history is critical. What we see from the red bar is that our model is sensitive to error propagation. Because we rely on the previous SQL queries, if we mess up something in these queries, we are unlikely to be able to copy it right. And so if we give access to gold standard previous queries, then we perform significantly better. I'm also showing here two follow-up works, one that uses an editing-like mechanism instead of our copying mechanism that performs slightly worse than our approach. And one that takes our approach. This is the green bar lineal, and what it does, it basically enforces syntactic constraints of SQL on the decoding process, so you're guaranteed to get a correct SQL expression, and this helps boost the performance of our system significantly by over 4 points. Okay, so I'd like to conclude by discussing some of the limitations of ATIS that are actually motivating some of our design of a CerealBar, which I'm going to discuss next. So first of all, ATIS evaluation relies on static corpus of recorded interaction in a Wizard of Oz settings. And this doesn't really reflect system performance or user behavior, because user behavior is really dependent on how the system reacts to their responses earlier in the interaction. Another thing this really requires live evaluation, but live evaluation with ATIS is really difficult because the Wizard of Oz setup requires a lot of domain expertise from Wizard, which makes recreating and scaling the setup very challenging. The expertise is also actually required from the users, and what some of the ATIS sites did is they showed the database schema or visualized it in some way to the users. And you can imagine how this really influences how the kind of language users are likely to generate. Now, this is actually a really difficult problem in collecting data for this kind of system. And some more contemporary benchmarks like CoSQL are doing the same thing. So they are showing the schema they're introducing the schema and the structure of database to the user. And in the one hand, this allows the user to really take advantage of the system abilities, but on the other hand, it also can potentially skews the language of the users to be more along the lines of what the schema describes. Another thing another problem with ATIS is it's very difficult to get natural and incentivized user engagement with a dictated, often overcomplicated scenarios. ATIS is still a very challenging benchmark and there is a lot of room for gain there, so I really encourage people to work on it and look at it in more depth. It's one of the most interesting semantic parsing benchmarks out there, even now 30 years after it was collected. Okay, so now I'm going to switch gears and I'm going to switch talking about CerealBar. It's a collaborative instruction following game where I'm going to introduce it, and then I'm going to discuss how language and user behavior evolve and change over time as users use the system. And finally, I'll discuss briefly about some of the interesting learning mechanisms that we introduced to CerealBar, where you learn to recover from cascading errors in like sequences of instructions. CerealBar is a situated collaborative game with sequential natural language instruction. This is the CerealBar environment. Each environment in CerealBar is procedurally generated randomly for each game. So each game gets a different environment. This game environment includes different types of objects. So we have passable terrains like grass or roads. We have impassable terrains like lakes and mountains. Different landmarks like houses, trees, lampposts, and different cards that are distributed around the environment. And these cards have different patterns. So for example, square or circle, or circles, rings, and bars here. Different colors like orange, blue, and black, and different counts of object on them, like specifically 1 object, 2 objects, or 3 objects. In the CerealBar environment, we have 2 players, a leader and a follower. And the follower is here on the left. This is the monochromatic figure, and the leader is on the right. This is the more colorful figure of the two. The 2 players, they play a game that is very similar to the card game set, if you're familiar with. The goal is to collect valid sets of 3 cards, where a valid set is a set where each color is unique, each shape is unique, and each count is unique. So each color, shape, and count appear exactly once. Appear once and no more. Each set is completed. Each set is completed gives the 2 players together 1 point, and this already reflects the collaborative aspect of the game. So let's quickly play set. So this is a set of 3 cards, and this set is a valid set because each count appears once, each color appears once, and each shape appears once. On the other hand, this set is invalid, and the reason for that is the count 3 appears twice. So the 2 players move around the environment and collect cards. They take turns with limited steps per turn, and they move around the board, and to select cards, they're just stepping on them. If stepping on a card flips its selection status. So if it's selected, if it's not selected, it will be selected. If it's selected, it will be unselected. When a valid set is selected, the cards disappear and new random ones appear. The agent gets a point and also gets more turns completing sets. So as you're doing better and better, you will have a chance to get more points and in our data collection process also actually make more money. So let's look at a specific, like a small example of these dynamics. So this is our leader and this is the follower, and this interaction is going to start with the leader collecting this yellow plus. Then the follower is going to turn around and get these like 3 red bars, and then the leader will get their turn. They'll pick the 2 pink stars, and this will complete the set. The cards disappear, and the 2 players received a point. Both of the agents in CerealBar, they select sets together. The leader instructs the follower, so they both act in the world by moving together, and the leader instructs the follower using a natural language, whereas the follower, their goal is to follow these instructions. So they can execute multiple instructions per turn or 1 instruction across multiple turns. And we introduce we design a gap between the 2 agents to incentivize collaboration. So first of all, the 2 agents have different level of observability of the environment. The leader sees the complete board, which means they can strategize and pick which and plan on which set of cards it's most efficient to collect right now, given the location of the leader and the follower. Whereas the follower only sees what's ahead of them. So they don't see all the cards, they have a very limited view, and they also don't see what the leader is doing. So they have to follow the instructions, otherwise if they will just collect sets on their own, they will conflict with whatever it is the leader is doing and sabotage the performance of the pair together. On the other hand, the follower has many more steps per turn, so they are the workhorse of this environment, of this game. So if the leader really has to use the follower in order to perform well in the game. Otherwise, they won't be able to get much done because they have so few steps per turn. Okay, so let's quickly see how the different perspectives look in CerealBar. So this is the same example we looked at earlier, but what I'm showing here is at the top I'm showing the crop of the environment that reflects the leader point of view, and at the bottom the first person, very limited observability of the follower. And the leader starts by giving a very simple, in this case, natural language instructions. Grab the 3 red stripes behind you. This is a simplified example just for illustration. So, and as you can see, the follower doesn't see the card. It's behind them here. So they will have to follow the instruction in order to collect it. And then the leader is going to do some actions. It's their turn, so they're going to grab the yellow plus. And then the follower turns around following the instruction, and they identify the card they have to collect, and they pick it up, and then the leader goes and collects the pink stars, and they complete the set. There are many possible tasks to study in CerealBar, including a potentially generation task, but the task that we're interested in is learning to map leader instructions to follower actions. So we want to learn this function that goes from that maps an instruction, whatever the user observes in the environment, so the follower observes, and whatever else happens in the environment, like leader actions, and we want to map it to a sequence of actions. These are discrete actions, so the follower can move forward, turn left, turn right, or indicate they completed the instruction. And the context is the history of the interaction and structural observations from the follower perspectives. In the models that in the model and learnings I'm going to show later on, we're making 2 simplifying assumptions that simplifies part of the problem, where we ignore the interaction history, which caps our performance, doesn't allow us to reason about context dependency in previous utterances, and we also assume full observability, which drastically simplifies the task, but still illustrates how challenging the complete task is. Okay, so the CerealBar scenario emphasizes 4 important aspects of natural language understanding in interaction. It has spatial reasoning, so the interaction is happening in dynamic 3D environment that keeps changing. It's a collaborative interaction, so it requires working together, the 2 players to work together, and this is really critical for success. There are sequential instructions here, and this includes dependencies between them, planning, changing goals, and instructions that include multiple sub-goals. And there is user interaction. So the user continuously sits in the interaction and interacts with the system. They observe what the system does, and they continuously adapt and modify their strategy. Let's look at a slightly more complex example in CerealBar. So this is an example that was collected from our human games, which is our data collection process, which I'll discuss more in a second. So in this example, we have the follower here and the leader here, and I'm putting here at the bottom in the large frame is the leader point of view, and at the bottom left is the follower point of view. The leader starts by giving the instructions: turn left twice and head straight towards the doghouse and look for 2 green circles to pick up. So it wants the follower to pick up this card here. And as the follower will start the execution, it actually goes a bit in the wrong direction, but it will quickly correct itself and move in the right direction. In the meantime, let's look at a more interesting example of interaction in CerealBar. So this is from our human games, which we collected during our data collection process, which I'm going to discuss in much more detail in a few minutes. So here we have our follower and our leader, and the follower starts by, and we have in the large frame we have the leader's point of view, and at the bottom left where the first person partial observability view of the follower. The leader starts by giving the instruction: turn left twice and head straight towards the doghouse and look for 2 green circles to pick up. So it wants the follower to go and collect this card here. And as the follower starts the execution, they move a bit in the wrong direction, but they're going to quickly correct this. In the meantime, the leader is going to collect this card here that we don't see that they plan for the set. And the follower gets the set, the leader gets their turn back. They move to collect this card, and collecting this card will complete this set, but they don't have enough steps to get to it. So what they do is they they don't want to miss using the follower in the next turn. So what they do is they plan ahead and they give the follower, and they gonna position the follower for the next card by telling it turn left and head towards the yellow hearts. So go to and collect this card, but don't pick them up yet. And I'll get the next card first. And the reason is, if the follower goes and picks them up, they will sabotage the current set that they are collecting. So the follower goes and positions themselves next to the card as the instruction instructs them, and then the leader goes and collects the card. The set is complete. The cards disappear, and new cards appear. It continues to the next one. It doesn't have enough steps to actually get to it, but it's positioned itself. And then it instructs the follower to now pick up the yellow hearts that I talked about earlier. So, but also move to the next, go and I'm already sending you to the next card. So I'm going to send you really, really far, to all the way to the other side of the board, to these cards here. So run past me towards the bush sticking out. So here, on the opposite side is the free green stars. So you're looking for this card basically, but you haven't been told to collect it yet. So the follower collects the cards and then runs all the way to the other side. The leader gets this card, and then the follower, and then the leader gets the card, gives the instruction. After you get that, so implicitly now I tell you to collect the cards we talked about earlier. Then pick up the three print crosses to the left and these two yellow stars, and we're going to continue for the next set. So the follower goes and collects the cards, the interaction continues. So there are several aspects that make instruction following collaboration very different from scenarios where the user doesn't operate in the same space as the system. The user actions are interleaved in system actions and likely depend on it, and the environment changes in unexpected ways that are not necessarily dependent on system actions. And these two things really complicate the kind of reasoning that the system has to do. On the other hand, there are some certain advantages for this, that not everything is lost on errors. Users are likely to redirect the system to recover. They can adapt their language or the task they are delegating. So if there is a task that I want to do and it's really hard to describe, I might decide to do it myself, while giving the system that has relatively simplistic understanding of language easier to describe tasks that maybe take more steps because it can move longer. And so there are certain aspects. in the design of CerealBar that when we designed CerealBar, we took into account and in thinking about some of the previous datasets like ATIS of MED tasks. So both CerealBar and ATIS, they focus on language understanding, and they abstract away much of the full dialogue problem. And you can see this in both CerealBar and ATIS having a one-sided communication channel in natural language. So the user gives instruction using natural language, but the system does not respond using natural language, it just behaves in the world. It either in ATIS generates SQL queries and executes them against the table, or in CerealBar just moves in the environments and select cards. But there are certain very key differences between the two that we in how we design CerealBar compared to ATIS. So in ATIS we have this evaluation using a static corpus, and this does not really reflect the real system performance or user behavior. On the other hand, CerealBar is really easy to deploy for live evaluation, and there is a very clear task success measure, basically how many scores you get, how well you're doing in the game, how many points you get. And this is indeed how we do evaluation on CerealBar. In ATIS, the Wizard of Oz scenario requires a lot of domain expertise that makes recreating the scenario very challenging and difficult to scale up. And this is partially why evaluation with ATIS is so difficult. In contrast, CerealBar is a game-like domain. It's very easy to learn, and we have a very quick tutorial that teaches a crowdsourced worker how to use it, and requires very limited expertise. It also doesn't require us any expose the users to anything that kind of like is sort of cheating the system by giving them an access to the internal schema of a database, for example. So we don't need this because it's a much simpler scenario. Another thing, and last thing, ATIS is very difficult to get natural and incentivized user engagement with dictated scenarios, where in CerealBar, user engagement through incentivized collaboration is really simple for non-expert users. And we can really just pay people by how much points they're getting, which really ties their internal incentives to the interaction in the game. And in that sense, CerealBar, especially in those last 2 points, that it's a game-like domain that does require a lot of expertise and user engagement is highly incentivized. It's really similar to the map task, but does it without really going all the way to a complex dialogue scenario. Okay, so as the CerealBar data collection, what we did is we collected human-human games using human-human games. And this basically gives you a Wizard of Oz setup, but without much of the needed wizard expertise. We recorded 1,200 successful human-human games with about 260 workers. Workers were doing both roles, so both leader and follower, so they were really aware of how things look on the other side. The games are fairly long, they're about 16 minutes on average with 20 instructions, and we collected the data, and the collected data shows the community is forming conventions and how the user behavior is dynamically changing over time. And I want to show you some of this analysis. So what we did is we partitioned the data into 10 deciles, where basically, because we collected the data over a long period of time, we can look at the games and when they happen and divide this period into 10 equal partitions. Each partition has a roughly the same number of all partitions have the same number of games. So what do we see here? So we see that the community relatively stabilizes. The number of active players, which fluctuates early on, is stabilizing in the later deciles, and we have fewer and fewer players joining. And this is for a simple reason that we just stopped qualifying new players to join the game. Not surprisingly, people are getting really, really good at this game over time, so performance improved. So the mean score per game significantly increased over time, and we can see it climbing from as low as around 3 to something like 13 in the last deciles. So followers and both, and this is because both followers and wizards so followers and leaders, so followers as wizards and leaders as users, they became much better. And we can see this by looking at this plot at the bottom. So what we see here is that, first of all, the shortest distance for instructions actually increased, illustrating that the leaders are giving more complex instructions that require the followers to travel farther. On the other hand, the number of access moves that the followers are doing is decreasing, showing that they're getting better at executing these instructions. And this potentially reflects the dynamics of the design dynamics that we expect in a user system adaptation. So we would like users, as they use system more, they get to know its abilities and what it can actually deliver, and they get better at operating it. This is what we see the leaders are doing. And on the other hand, we would like our systems to adapt to users and execute what they want better over time. And this is what the followers are doing. Now, one of the most critical aspects of CerealBar and of the data that we observe in the data is that the language actually changes as the game improves. So the game is improved, the performance in the game correlates very heavily with changes in the language. So here I'm showing at the top, this is the same graph that we saw earlier of the game score improving over deciles. And at the bottom, what I'm showing is like very shallow statistics about the language. So we see the vocabulary size. This is the blue bars. It's increasing over time. So the vocabulary in the 10th decile is significantly larger than in the earlier deciles, showing that people are using more complex language, at least lexically. But very quickly we're going to see that it's actually more than that. So this was the number of instructions. The vocabulary size was the green one. The number of instructions is also increasing, and this is not surprising because as you get higher scores, you are getting more turns to execute them, so you can give more instructions. So the vocabulary size increases, indicating that leaders are changing their language over time. The language changed, so we also observe changes in the instruction length. So instruction length starts relatively short. So this is this blue bar here. The mean instruction length is increasing and then stabilizes. Whereas the words per card event, so the words that are required to create a card event, are decreasing, and are slowly decreasing over time. Also, we are observing that the number of instructions per card event, so the number of instructions that are required per card event, is decreasing, reflecting the fact that instructions are packing more and more card events, so sub-goals in the same instructions. So instructions deliver more information, and leaders require less words to get to cards and packs more information into each instruction. And this actually is in contradiction to some of the results that we see in other collaborative scenarios, and I'm going to discuss this in a second. Okay, we also observe that as the instruction length increases and stabilizes, the language becomes syntactically more complex, at least as we are observing it as far as the branching factor. The syntactic branching factor, this is the orange curve, increases and follows a similar trend to the mean instruction length. And we can also see, and I'm not showing it here, that higher scoring games actually have a higher branching factor. So higher scoring games are qualitatively, syntactically different than low scoring games. And on the other hand, another measure of syntactic complexity, maximum syntactic depth, is relatively stable throughout the game. So there are some key takeaways that I want to take away from this linguistic analysis. So the community performance in CerealBar increases over its lifetime as leaders' language becomes more complex. So not only the leaders and the followers are becoming better, so the users and the systems are becoming better, it's also that the language that the leaders provide, is substantially different. It becomes more complex as far as the vocabulary, the length, and the syntax. And this really illustrates the dynamic nature of users and language in interactive systems. As users are convinced the system can do better, they will try to achieve more by giving it more and more complex instructions. So they're trying to maximize their benefit. They're trying to maximize their utility in this sense. And this is actually in contrast to trends observed in convention formation analysis in reference games. So in reference games, they have a pretty different setup where two agents are collaborating, where one agent is trying to describe an object out of a set of objects, and the other agent has to point to that object, so resolve the reference. So in reference games, every turn, every sentence is focused on a single choice and a single goal, where in CerealBar, leaders actually have the ability to pack more goals into every instruction they give. And they are doing it increasingly as the game progresses, and they are more convinced of system ability, and they're also becoming better in the game. So the conclusion, from reference games, the analysis concluded that language convergence is actually becoming simpler and more lexically uniform in the game. So the vocabulary increases and the length of utterances, the vocabulary size decreases and the length of utterance decreases in these reference games over the community lifetime. In CerealBar, we see exactly the opposing trends. Okay, so I want to show you a very quick model on CerealBar just so I can talk a bit more about learning. So the model that we're using is based on the prediction visitation network that we introduced in a Blocky et al. Paper in 2018 for a robotics task. It's a two-stage neural network model that is fully differentiable, but has this explicit plan generation in the middle, and these plans are cast as predicting distributions over positions in the environment. And then there is the second stage that's this recurrent action generation to follow these plans. So how does it look? So you get the observation and the instruction, and you have a neural network that generates these distributions over positions in the environment. We are generating 4 distributions: the distribution, the trajectory location that you have, the position that you have to visit during your trajectory. Goals, these are cards that you want to select. Cards to avoid, it's very important not to select them, so we're actually modeling it, and position in the environment that you cannot pass. Given these distributions, which are just generated over in the global reference frame of the environment, we take these distributions and we crop them and rotate them around the current follower location, and then we put them into an RNN to generate the actions in sequence. After every action, we recenter and re-rotate and recrop around the updated position of the agent. Okay, so for the training data, we have these human-human recorded gains that we collected on using the Wizard of Oz scenario on Mechanical Turk. And because of the interface, each instruction is exactly aligned with the sequence of actions the human follower performed. So it's very easy to generate gold standard visitation distributions. And this allows us to basically use supervised learning, where we have this auxiliary objective in the middle that allows to initialize both stages separately with supervised learning, because we have basically these gold standards plans. And then after we do this, we train both stages together to fine-tune them, and at the same time we train to recover from error propagation between instructions. So how does it look? Just to visualize this, so we have on the predicted plans here we have a cross entropy loss that we get from the gold standard plans, and then we use teacher forcing for the action generation. So we have these like 2 objectives that train these 2 parts separately, and then we fine tune the whole thing. A key challenge, and this is something that I want to focus on a bit more, is that there is actually no opportunity in the data to learn to recover from errors. And what we want to do is we want to learn to recover from errors where there is error propagation between instructions in sequence. And so if we fail to execute a specific instructions, we would still like to have a chance at executing the next instruction, even though we are starting from the wrong start state. So our approach has 2 parts. We augment the data with their data recovery examples, and we train the model to reason differently about these examples in order so not to sabotage the learning of the language. And I'm going to show an example of why this is important, how this works. So these are 2 examples in 2 consecutive instructions in CerealBar. The first one is turn right and go down the road to the intersection with the tree. So we want to go down here. And the second one is pass the yellow house on its left and grab the free blue triangle. So we want to go like this. So these are the 2 instructions. And something that you can imagine happening in inference time is that maybe you are not really executing this first instruction right. And instead of going down this road, you are going up here. Somehow you get to here, and it's an intersection. It has trees. It's a good place to stop. So you're just going to stop there. But this means that you're actually not in a good position to start the next instruction. So what we do is relatively simple. We create a new recovery example that starts from the bad start state here, and using a very simple planner to collect the cards we're supposed to collect gives us a trajectory. So this is a new example, and we can just simply throw it into our database and into our supervised training set. We generate these by doing rollouts during training. We can add them to our training set, and that would be the end of it. The problem is this actually can sabotage learning. And the reason for that is that these new examples not necessarily aligned with the language. So for example, here we see that the instruction pass the yellow house on its left and grab the 3 blue triangles is referring to a yellow house is supposed to be, and you're supposed to walk on the left side of the house. Whereas from here, the salient yellow house is this one, and we're actually passing on its right. So if we just add this example to our training data, we are actually confusing our model in this specific case with regard to the very important concept of left and right. So we really need to reason about this differently. So what we do is we add a binary classifier that is looking at all the internal activation of this part of the network that generates these plans, and using these internal activations tries to classify if this is a recovery example or if this is not a recovery example. And we use a cross-entropy loss and try to maximize the performance of this classifier during training. During testing, of course, we remove this classifier. But what does it mean to be able to classify this correctly during training? It means that these internal activations here, they look differently for recovery examples versus not recovery examples. So the system is able to look at its start state, see the mismatch between what is specified in the instruction and what is in the environment, and then reason about and then distinguish how it reasons about this instruction compared to instructions that are completely right. So for learning, the way we work, the way learning process works is we alternate between updating the model parameters and collecting new examples for error recovery by doing inference. Okay, I want to quickly conclude with some results. So these are results on live games. So after data collection, we went and conducted another 200 games that are mixed between human-human games and human agent games, where we didn't tell the human leader if they are playing against another human or against playing with another human or with our agent. And what we see here and what we are measuring is how many points they get in the game. So this is task performance. And as you can see, our agent performs significantly worse. On average, they're getting about half the points that the Wizard of Oz human games are getting. This is, of course, to be expected. But it does show us that they're able to still effectively collaborate with the agents. And the humans and the human leaders that adapted to the system well, they were able to actually perform really well. And the max scoring game that we had between a human and an agent partner was 14 points, which is significantly higher than the average game between humans. We do observe that followers, this adaptation shows up in language. So in general, we observe that although we didn't tell leaders which agent they are playing against, if it's a human or if it's our agent, they do understand that pretty fast. And what they do is they simplify their language. So they actually use shorter sentences and a smaller vocabulary. Okay, so let's briefly summarize. I talked about ATIS, where I focused on context modeling for natural language understanding and how it exposes opportunities to reuse computation by copying work that you already did in previous utterances. I then discussed about some of the limitations in the benchmark, including the use of static evaluation, the need for expertise on both the wizard and the user side, and user engagement for natural interaction. This motivated the second part, where I discussed CerealBar. It's a collaborative instruction following game where we get engagement for collaboration. We have low expertise bar and a very strong incentive structure that's designed to really elicit like high quality natural language. I then discussed how the user language and behavior changes over time when interacting with the system, and how it really depends and how it's different from what we see in other natural language collaboration data sets. And finally, I talked about learning to recover from cascading errors between instructions by injecting failures into a supervised learning algorithm and learning how to reason differently about recovery efforts. So the work I described today was done by Elaine Sor, my student, and with a lot of the game design of CerealBar done by Claudia Yan. And the language analysis I showed was done by Anna Effenberger, together with a significant contribution by Eva Yan and Ria Sinj, and a number of other collaborators. You can go online to play with our agent, and thank you very much for listening. And I'm looking forward for the discussions and the question at the workshop itself. Thank you.